I'm rotating. Kids, we are going to do a practice problem here. So here's the practice problem. Solid ball, that's important because remember, a solid ball, that tells you that the rotational inertia is going to be 2/5 mr squared. Okay. Sorry, you can't really see it, but yeah, it's 2/5 mr squared. It's moving 5 meters per second. It's rolling without slipping. That's also important. Because remember we talked about that, and if you don't get it, feel free to go back and look at that previous video about something rolling without slipping. That means that there's hardly going to be any heat along the ground and then up a ramp, and we want to know how high does the ball go. So the key to any problem in physics is, number one, to draw a picture. So let's draw a picture of what is happening. So I have a ball. It is rolling along level ground, and then it's going to go up to some certain height. Now, if you want to be able to do rotational energy problems, first off, hopefully it's pretty obvious that, hey, I'm going from some type of kinetic to potential. So if I'm converting energy, I should be thinking energy and conservation of energy. But we need to draw a good picture. So here's what I mean by a good picture. If I just draw this, it seems like, well, it's not moving over there, it's not moving over here. So let's talk about what a better picture would look like. All right, well, it's moving along at 5 meters per second. But that's still not a good enough picture, because this, to me, if I was looking at this picture, would seem like it has just kinetic energy 1/2 mv squared, and then potential energy here. But it doesn't. It's rolling without slipping. So now I want to include this in my picture. So this is going to say, hey, it's rolling. It has, rotational kinetic energy, and it's moving along regular kinetic energy potential. Okay, so I'll call this my point A. I'll call this my point B. And if I go from A to B, we would just set up our equation. We'd go, all right, so what type of energy do I have here? Well, I have translational kinetic energy. That's 1/2 mv squared, plus rotational kinetic energy, 1/2 I omega squared. And then over here, I would have UG. Now, my system would have to be the ball and the earth and the surface. Okay? So nothing is going to be leaving my system. In fact, okay, even though the surface and friction is part of my system, remember we talked about before, if it rolls without slipping, there's very little heat that's produced. So equals. Everybody good? That's the hard part. And then we got to do some algebra. So let's do some algebra. This is going to be 1/2, I guess this is still physics, 1/2 mv squared. This is 1/2 I omega squared. This is going to be mgh. Now, I give you 5 meters per second. So you might be, well, let's see if I can convert this to a v, a linear speed. Well, you can. Remember to do it. We're going to draw a little circle, and we're going to say, hey, if I was going all the way around a circle, the distance I traveled would be 2 pi r. The theta that I would sweep out would be 2 pi, which means d is related to theta by theta times r. If I divide by t, I get v equals omega, because theta divided by t is omega, times r. So if I solve this for omega, I get omega equals v divided by r. All right, let's plug stuff in. So I get 1/2 mv squared plus 1/2, I got to use my I equation, my rotational inertial equation, 2/5 mr squared times v squared over r squared equals mgh. Hey, look, mass wasn't given in the problem, but that's okay. Bye-bye, mass. And then if you look, bye-bye r squared. So I end up with 1/2 v squared plus 1/5 v squared equals gh. And then doing your handy-dandy math, you get, well, 0.5 plus 0.2 is going to be 0.7 v squared equals g times h. And if we do some algebra, let's see, 0.7 times 25, because 5 squared equals 17.5, divided by 9.8, and you get the height to be 1.786 meters. So, about 1.8 meters high. So it would roll about 1.8 meters high. There you go. Oh, let's make sure you can actually see 1.8 meters high. Bucky!